Okay, so I'm going to talk about the NOMAD archive. So what I'm going to explain first is how we transform the data from raw data, from these input-output files to the metadata we use in the archive. So as Jungo just explained, in the repository you can do very nice things like you have stored the input and the output file, you have web-based access, you can search in the repository, you can download, you can upload your data, you can share the data, and you can have the data there for many years, and also you can reference your data so you can cite the data you use. But this is not perfect because sometimes you have problems. For example, a typical problem is, okay, I have all these calculations from one code, but I need another calculation that were computed in another code, and I want to combine all these calculations. Usually that's problematic because different codes, they have different notations, different units, different definitions, and not all the codes are computing the same thing. So usually that's a problem. So how can we solve this problem? Well, first of all, just an example. For example, this is a typical file from FHMs, and maybe I'm interested in this quantity that is vector. So I can code something, so I can obtain the values, put it in a matrix or whatever, in whatever language I use. I define a function and I compute the volume. That's okay for this code. But what happens if I have to do the same with another code? Then probably I have another format here, I have to do another regular expressions, I have to do other things, I have to do this with 30 codes, a lot of work. Also probably the units are not the same, so that can be a lot of work, mostly if I don't know the codes. Okay? So what can we do? We can define like a common language. We call this meta-info. In this common language, we are going to use standard format, standard units that are the international ones. We are going to use a fixed notation. It's going to be independent of the code, so we are interested on the physics, not on the implementation. And also, in this way, it's easy to combine things, because what we store here, the metadata we store for the meta-info, is the physical values. And the physical values, if they are in the same units, they should be equivalent. Okay? So how can I know about the meta-info in NOMAD? You can go to this web page that I don't have the URL here, but you can go to the NOMAD web page and it's there. So essentially I can query for all the meta-infos. I can just put here what I'm interested in here. I get the list. Then I see what is the definition of this meta-info, what type of data is, if it's a matrix or it's just a number. And also we have these funny things. This, if it's a section or a number, I go through this later. So the idea of creating this meta-info is that all these quantities we are interested in about properties of the materials that are encoded in all these input-output files are going to be stored here independently of the code and all in the same format. Okay? So first, we are going to explain how we structurize this meta-info. So the idea is we are not going to use let's say a normal relational database. So we are going to use this nested format where this section, so the starting point is always a section run that refers to the calculation. Then we have these other sections that are included that are in the language of a relational database. These are like tables, okay? And we have several sections that contain several different information. So each metadata with a concrete value that is the final value is contained in one specific section that, well, you go to the web page, there is a diagram here, and you can see in which section belongs and how it's related, okay? We are going to see all this later in the tutorial. So here you see also that there are relations between sections. So probably most of the information that is contained here in this section single configuration. Okay, you need to understand this, you need some information that is contained in other places, but it's redundant to write everywhere. So you just have to refer to the proper section before, and you get the data. Okay? So that's how the information is stored. So what we do is we extract the information from the input-output data, and we create these files with this structure containing the metadata. So now I'm going to explain briefly how we do this. So the first thing we do is we take the data from the repository, the raw data, and we zip in this bucket format. This is just a way to be sure that what we copy from the repository contains what because we are going to store here forever, and this raw data should be immutable, so it never changes. And it's going to be there in a hard disk for many times, so it could be corrupted. So to be sure that it's containing the proper information, we use this bucket format that contains some files, meta-info, some manifesto files, saying that, checking that we can be sure that what we have there is what we had 10 years ago. Okay? Also, we sometimes, because you say, okay, I'm going to upload all my data, and this is 3 terabytes, and someone wants to download all your data. This is quite bad if you have a normal internet connection. So we typically split in smaller folders, so you can just download a single part or everything as you want in this raw data. And we also create an identifier for every single calculation. So if you want just one, you can easily go to the single file. You have access to only for open access. All what I'm going to talk about here is only for open access. We don't process the restricted calculation. You can download directly in this web page. So here you have access to all the raw data we have in the archive. If you want to download it, this is similar to the repository. And then once we have this, we need to remove the code dependence. We call this parsing the data. Okay? For example, you ask if you can create a converter for your code. Essentially, what we do is we create one thing we call parser for each code. And this code is going to extract the information we need and create a file we call archive that contains the metadata. Okay? So in principle, if you want to do that, there is some rules to how to create the converters. You can do it in Python or Scala, and we can help you to do it. Okay, for example, this is one of the main problems of this project, because in order to do this, you need to know the code so the structure of the input-output files you are using that are specific for each code, and you also have to understand about physics. You have to understand what are you parsing, what is the meaning of each number appears in the output. So this is a lot of work. Also, sometimes, depending on the code, is very time-consuming. So if we want to parse terabytes, you need to consume, you need a lot of computing power, and we have to improve also the parallelization of this process. Finally, once you have extracted the data, and you have the data that was already contained in the calculations, maybe you can add more data. So you can take the original data you have there, but you can compute another quantities in terms of that, because you have programs that can do that. And if they are supported by us, we can include this new data in these archives. That's what we call normalizations. So for example, if you know that, okay, taking all this metadata that I have in the previous step, I can run my algorithm for all the calculations and create new properties, we can add this also here. I mean, it's not that, okay, I have the data, I compute something for me, and I use it. If it's something useful for everybody, we can also add this to the archive. Okay, for example, this is some of the quantities that are already added to the normalized data, but it's also that we are reaching more and more, and if you are interested in any of us, in any new quantity, you should tell us. Okay? So this is a bit the flow of what we are doing now. So we start with the uploaded file by the user in the archive. We split and bag the files in these archive files. Then we parse. This parse assignment means we have to decide for each file to which code belong and to produce the proper parsed file archive. And from here, we assign which normalization are going to apply to this archive and produce the normalized archive. Okay? But the next step is having the data is fine because you have the data stored somewhere. But the other problem is you have to give access to this data to the people. Okay? And when you have terabytes of data, it starts to be a problem because handle this with a normal database is problematic. So you have to go to a more fancy technologies. So here we have the normalized archive that is the starting point for other projects like the analytics or the encyclopedia. And in order to give access to this, we are now using Elasticsearch, that I'm going to say a few words later, to explore the content that is, to explore what is contained in the normalized archive. To use Elasticsearch, we develop an API so you can easily query what do you want from the normalized archive, and we tell you what do we have and how to obtain the data you want. Also, you can directly access to the normalized archive if you know how to do it. Maybe if you are more a technical person. And also with the analytics toolkits that you are going to use is useful to use our API. So just a comment about the data we have in the archive right now. We have more than 9,000 files, zip files, coming from the repository. So this is like 16 terabytes that you have from the raw data. So when we extract the metadata we want, we finally got more than 5 terabytes of actual data. So this is not just text data with comments and so on. So this is physical numbers. We are supporting 90 codes, 29 codes right now, and 14 are under development. And to have an idea, we are extracting around 800 million of metadata from all the calculations. So it's a lot of information you have to handle. This is the time evolution of the total energy calculations in the archive during the years. You see that this summer we had a lot of activity with AfloLib and OQMD and materials project that is cut there. So that was a huge improvement for us. Okay, so now I'm going to explain a bit how to extract data. So once we have the data, we need tools to extract the data from the archive. So we are developing an API. So an API is just an interface that allows you to communicate with the data in an easy way, okay, using the web. So we developed 3 services right now for the API. One is the query, the resolve, and the download. The query is where you just ask what do you want, and you get where the data are. In the resolve, you can explore the data that you query for. And in the download, because in the query you are going to get many results. So in the download, you are going to get like the address of all these results if you want to do a complete analysis for thousands of calculations, for example. Okay, so now let's go one by one. So for example, for the query, you have to use this URL, this address. So it's the Analytics Toolkit web page. You start with API, and then you say query. Then this is, for example, a typical query. You say, OK, I want the codes that with the program name this one, and that contain these elements. OK? So when you do this in your Firefox or whatever you use, and then you get something like this. OK? This is ugly, but later I'm going to show you how to use this in an easy way. But if you are a developer, probably this is very useful for you. So essentially, you are going to get a file name. So this file name that you can use later is going to download the whole query. And you can also see a small sample of what we found. So this is our ID. So with this strange string, you can identify the calculation in NOMAD. And you also have some properties about the calculation, like the system composition and so on. Okay? So after that, for example, if I take this line and I go to the API resolve, so I use the same as before, but I write here resolve, and I wrote this horrible thing. Then what I got in Firefox, for example, is something like this. Here is all the information parsed for that calculation. And here you can explore all this metadata, the values, and so on. So you have access to the whole calculation in a structure, in a way that is completely ordered and according with the meta info. Okay? So you can check this, okay, this is what I'm looking for. Now I want all of these calculations. So then you can go to the download service. So you write the same, you write download, and you just write the name of the file that appear here. Okay? And you can download the zip that is going to give you the URLs, all the URLs, or you can, if you have access to the NOMAD data, you can also download in JSON format, and then you have access directly to the data.
Can I quickly ask a question?
Yeah.
Is there any reference when I make this query to the data from the repository? So do I know, can I find out from which data set from the repository it was, or is it reconnected?
No, it's connected. Actually, you have, well, it's connected now in a complex way. We are simplifying this. Essentially, we are creating a unified ID for all the projects. So now we have this for the archive. If you know how to, you can translate this one to the one in the repository, but we are going to do it simpler. Okay? But yes, in principle, it's going to be the same data, and in principle, you can have exactly the same. Okay? Also, we are working, this is still far to be done, but for example, many of these data are from Aflowlib. So the idea is, okay, if I have this calculation here and I want to know the same ID that the people from Aflowlib is using, we should be able to provide that. Okay. Okay, so this is useful if you are a developer, but if you are not, probably you prefer something like this. Essentially, you go to this web page that we are going to use in the tutorial, and here you are going to say here, well, if you type, you display the options and the possible value. You say, okay, program name equal FHAMs, atom symbol this, you query, and then you get the results. These are links, so if you click here, you go directly to the resolve. If you go download, you download the file. So this is easier if you want to use it. But the API is open, so if you are a developer and you are interested, you can do whatever you like. Okay? So just a few words about Elasticsearch. So we are still working in improving the query format, exploring another technologies, but Elasticsearch is quite nice because it's very fast. And the idea of Elasticsearch is a cluster thing. So if you have more data, you just have to add more computers, and it's going to scale horizontally. You have clients for all the more used programming languages. Even we don't have access, at least externally, to our Elasticsearch. And the idea is these technologies are based on this invert index that allow you to query very fast in whatever search engine. So the important is how you define your index. Right now, our index is something like this, where you can query if whatever metadata is present. So if you say, okay, I want all the calculations that contain this metadata, you can query. You can query, okay, I want all the data uploaded by this person or by this program containing this atom symbol or species or whatever of these properties you can query. And we are adding more. Okay? So that's what we can do right now. Using this, you can query the archive, and you can get results like this. Like, for example, how many total energy calculations we have, which are bulk crystals, surface molecules, or other properties. Okay? So you can do a stat. So because the point is, once you have terabytes and terabytes of data, it's important to know what do you have. For example, you asked before, okay, but maybe 90% of what I have is the same, and I have only 1% what I'm interested. Okay, then maybe you can create a project saying, okay, what do we need? So I want to generate new data. So you can come here and say, okay, what is what we don't have, and focus on that part if it is needed. Okay, but first we need to know what do we have, let's say. Okay, so here you have the same distributed in the codes, in terms of codes. Or, for example, you can query the calculations in terms of the crystal system. And this kind of plots or information you can also query here in this web page, where you can play a bit with the graphs. Okay, so that's fine, but that's not all. We want to improve this. So now you have to go to the resolve. You can explore and you can get the JSONs. But this is still more complex for many people. So ideally, what you want is, OK, I have these conditions, and I want to get this, and these properties. So that's going to be our next step. In order to handle this problem with this amount of data, we are exploring using big data technologies like Spark or Flink, or, for example, Emma language that is developed by people from a big data center in Berlin that is a framework to combine any of these two languages in one. And we are also thinking how to implement a storage format that scale properly for these big data technologies. So as conclusions, the first point is not only important to have a huge amount of data. The data should be structured so we can use it and it can be combined. Once we have this, we can allow other people using our data. And what is more important is not only a matter of having many information. You should be able to use all that information. So we have to provide easy tools so the people can just query what they want, extract the information, and do the research and avoid the technicalities. OK? And that's all. Thank you.